In this video, we're going to start to see how to measure the properties of a transverse vertical isotropic rock. First, we're going to get started with the static properties, and then we'll talk about the dynamic properties. For the static properties, we usually use an axisymmetric triaxial cell for measuring the stiffness and elastic properties of the rock. In an axisymmetric cell, we got samples in a cylindrical shape so that we can apply a three-dimensional state of stress, here simplified to 2 dimensions, in which we have a radial stress and an axial stress. These two, the radial stress and the axial stress, can be different, but notice that in 3 dimensions, if the radial stress is the same, that means that the two of the principal stresses perpendicular to the axial direction are going to be the same. In the conventional method, we usually apply what is called the deviatoric loading stress path. And in this deviatoric loading stress path, we keep the radial stress constant and we increase the deviatoric stress, sigma A minus sigma R. Since the radial stress is constant, then this is equal just to the change of the axial stress, where the axial stress is equal or larger than the radial stress. Usually the experiments start with the axial stress, effective axial stress, equal to the effective radial stress. Okay, let me emphasize that this is very important to the method. Ideally, we would like to measure these properties of a TVI medium, and we're going to see the reasons for that later, on a prismatic rock, but it's very difficult to cut a sample in a cube, and it's even more difficult to apply the loadings. So that's why we use cylindrical rocks and we apply this axisymmetric loading. All right, so we're going to have two options here in order to cut our rocks depending on the orientation of the rock. And these are going to be either in vertical direction, perpendicular to bedding, and this applies mostly to sedimentary rocks, or in horizontal direction, which is in the direction of bedding. Before we go into detail about what this all mean, let me just show some examples in order to justify the lection that we have done. And right here, we see some examples of real rocks which are layered. Again, this happens mostly in sedimentary rocks. And here we can see that even at the millimeter scale, we can have this layering that results in anisotropic properties of the rock. You could also go, and we're going to see later, that this goes also at the micrometer scale, that you can also observe layering. And even if you go to larger scales, like for example in sequences of rock, you can also see that packages of or sequences of rocks, they can also exhibit this type of layering that is going to result on something with something that resembles a vertical transverse isotropy. Okay, so since we have already motivated this discussion, let's see now how we measure these elastic properties. Okay, the first thing that we can do is we can apply here an axisymmetric loading to this vertical sample. Let me zoom in here so it's clear that I'm just talking about the vertical sample, so that I apply a stress in direction 3, which is perpendicular to bedding, and I measure a strain in direction 3. The relationship between these two, keeping the radial stress constant, which in this case is going to be sigma 11 and sigma 22, is going to result in the vertical Young modulus of the sample. This is very similar to what we did before in order to define the Young modulus, but now notice that there is a directionality. The vertical Young modulus is going to be perpendicular to these layers that usually in a sedimentary rock are going to be horizontal, and that's why it's called vertical. In addition to that, we can measure what is called the Poisson ratio for vertical planes, and this is going to be equal to this can also be defined as here. I'm just making an average, but it's going to be defined as negative of the variation of epsilon 1 divided, and this is going to be the radial expansion divided the axial contraction, and in a perfect VTI medium this should be the same. The equation I have on the left is an equation I have on a paper in which we were approximating this Poisson ratio by taking an average, but in an ideal VTI medium the definition is going to be what I wrote on the right in blue. All right, so what are these? These are the Poisson ratio that result from applying a stress in direction 3. So now this is the same experiment as the one that we use for measuring the vertical Young modulus, and measuring expansion in direction either direction 1 or direction 2. Again, keeping the radial stress constant. And you may expect also that this Poisson ratio, the Poisson ratio, actually this one is called Poisson ratio 1,3, is equal to the Poisson ratio 2,3, because it's because of the axisymmetric symmetry. We should expect those two values to be the same in direction 1 or in direction 2, because the sample is symmetric with respect to the axis number 3. All right, so now we have measured 2 parameters, and remember that for a VTI we need to measure 5 independent parameters in order to fully characterize this anisotropic medium. All right, the next choice is going to be to obtain a sample of this VTI medium, but now in horizontal direction. Notice that I have kept here the direction of the axis in direction 3 to be the one which is perpendicular to lamination, and 1 and 2 parallel to the lamination. So this is the case, and now if I were to apply an axial load, notice that it's not going to be any more sigma 3,3, but it's going to be sigma 1,1, at least in this particular case. And if I measure a shortening in direction 1, what I'm going to get is the horizontal Young modulus. I could do the same for the sample drill in direction number 2, and I would obtain, because of the symmetry, the same horizontal Young modulus. And if I were to measure the expansion now in direction 2 and in direction 3, notice that it's not going to be the same, because of the anisotropy of the medium. You would expect the expansion in direction 3, and which now this one is Poisson ratio 3,1, or we're going to see it's equal to this vertical Poisson ratio, to be different than the expansion in direction 2. And this is Poisson ratio 2,1. Why? Because the medium is anisotropic, and you shouldn't expect the expansion in direction 2 to be the same as the expansion in direction 3. So these two now are going to be different. It's not the same as before. But notice that this Poisson ratio 3,1, we already had it before, because this one is going to be equal to 1,3. So actually, we haven't measured a new Poisson ratio. it should be the same as the one we measured before. So we just added two new coefficients to our equations, the horizontal yaw modulus and here the horizontal Poisson ratio, which links expansion in direction 2 with respect to 1. And it will be the same as the one you would expect for an expansion in direction 1 due to a load in direction number 2. All right, with the conventional method, there is not much really that we can do in order to fully measure the VTI coefficients of the anisotropic solid. So at the end of the day, what we're going to have is just from here 4 parameters. But we're missing one, right? There are some other methods that may use a sample inclined at 45 degrees in order to measure an additional parameter, or use a more complex stress path in order to measure these static properties. The one that uses the 45 degrees, it's a little bit difficult sometimes to analyze, because as soon as you add some deviatoric loading, you may be reactivating and failing some of the interfaces, and then the solid is not going to be elastic anymore. So you need to be very careful in order to apply such method. There is another method that has been recently published, and let me find the paper. It is right here. Let me share the reference with you, which I'm also going to put in a link in this video. This is the URTEC paper 2206. And in this paper, the authors show how to, it's a very nice paper, I recommend you read it, how to combine different loadings and stress paths in order to fully measure the VTI coefficients of an anisotropic rock. So if you depart a little bit from the conventional stress path, then you can get to measure these 5 independent coefficients. But we're not going to see that in this class. I recommend that you read the paper in case you're interested in that. But remember that there are some other options in order to fully define these static parameters. Why we call it static? We call it static because we are using the triaxial method, in which we are applying strains which are in the order of 1/10,000 to 1%, and the loading is quasi-static, or it is applied very slowly. That's why these are called the static properties. All right. Let's see now how we measure the dynamic properties of a TVI rock. And for the TVI rock, what we're going to do as well is we're going to use this conventional method. Let me bring a copy of this over here. In which we're going to measure wave velocities that start and finish in end caps in this same triaxial cell. This is the conventional method, and here we can have piezoelectric transducers that apply a P wave that goes through the sample, propagates, and you measure it with another piezoelectric crystal on the other end cap. And we can also apply a shear wave that is going to cause also a shear wave that travels through the sample, and you measure it in the other side of the end cap. This is the conventional method, and this is the easiest method to apply in order to measure wave propagation. Again, we're applying this to a cylindrical sample, and it's going to depend on which sample you use and what is the direction of your rock to interpret what are these P waves and shear waves. So let me add here that this is the conventional method, and I'll talk a little bit later about other non-conventional methods as well. Okay, so let's use this now conventional method in order to identify what are going to be these P and S waves. Okay, here we have the same samples as the one before, same orientation, same everything. And what we're going to see is what these P and S waves are. So let me respect my colors that I used before. First of all, if I send a P wave that goes through the sample in the axial direction on a vertical sample, this is going to be a P wave that goes in direction 3 and produces a strain also in direction 3. Remember that this goes by the name of uniaxial strain, and it's just a strain in direction 3, not in 1, not in 2. And in that case, if I have such a wave, what I'm going to recover is directly the stiffness parameter C33. Why? Because I'm just causing a deformation due to a change of stress in direction 3. And when you isolate that in the stiffness matrix, you see right away that this depends only on C33. And C33, by using the equations of wave propagations, we know that this is going to be proportional to the mass density of the rock and to the square of that P wave velocity. Usually in the laboratory, what we measure is separately the density, just by measuring weight and dividing by the volume. And we measure on the other side the P wave, and combining these two, what we can obtain the dynamic stiffness coefficient in direction 3. What would be now the result of an S wave? For an S wave, here we have two options. We can either send an S wave that produces a shear strain in direction 3-1 or in direction 3-2. So that's going to mean that if this is a shear wave, again, remember that the wave is traveling in the direction of in the axial direction, from end cap to end cap. Let me bring back this, bring to the top. Why do I do that? Maybe here. Bring to the front. Okay, this is our S wave, and this is going to depend, as we were saying, if it produces strain in direction in the plane 3-2 or in the plane 3-1. So if the shear wave is producing a strain in the plane 3-1, this means that, let me draw the deformed configuration. This is going to look something like this, and that shear strain will correspond to the plane 3-1. But remember, it's going in direction 3. I could also have a shear wave that produces a deformation in the plane 2-3. And this is going to be, this is becoming quite difficult to understand in 3 dimensions. So let me add the axis in order to help that. So this is 3, this is 1, and this is 2. if I had the same axis, but now I have a deformation in the plane 2, 3, then I will have the following. In the form configuration, this should look something like this. But notice that because of the symmetry, these two would be the same. Would be the same value because the stiffness in shear stiffness in direction 3, 2 is the same as the shear stiffness in direction 3, 1. So this is equal to the stiffness coefficient C44, which is the shear modulus, times BS either 3, 1 square, which is equal to the other one in perpendicular direction. All right, so now we have two elements of the stiffness matrix, 333, C33, and C44. We can also apply the same method with end caps and waves going through the end caps for a horizontal sample. And if, for example, we do this for a sample drill in direction number 1, then the P wave, in this case, if it goes in direction 1 and produces strain uniaxially in direction number 1, is going to be VP11, and this is going to give me the stiffness in direction 1, C11, the normal stiffness. What about the shear waves? Well, it's similar to the case before. For the shear waves, I could have those which are going either causing strain, a shear distortion in the plane 1, 3 or in the plane 1, 2. But now it's not going to be the same because the shear stiffness in the plane 1, 2 is not the same as the shear stiffness in the plane 1, 3. Therefore, if I, for example, have this shear wave to cause a shear strain in the plane 1, 3, let me try to draw that to see if I can make it and give to that a meaning in my drawings. This is going to be VS13 going through the sample, of course, and this is going to cause a strain in the plane 1, 3. I will recover C44, and this is the same property that we had before. The new property that I'm going to have is the one for the shear wave that propagates in the plane 1, 2. And now I'm recovering the shear stiffness in the plane 1, 2, and this is C66. Okay, so far we saw that this one, we already had this one. So similar to what we had before, we just have 4 stiffness parameters so far. With the dynamic method, it is more trying to find a good word to say this, but I would say it's a better representation or a better case to use now a 45-degree oriented sample because the deformations are very small and the changes of stress are very small, such that it's very unlikely that we're going to reactivate or fail in shear some of these planes. So opposite to the case before in the static case, in which by applying a deviatoric loading we could fail these interfaces, with the sample oriented at 45 degrees and just applying wave propagation, it's unlikely that that's going to happen. So in this case, the theory applies a lot better. And what we're going to do here is we're going to use a P wave that goes through the sample from end cap to end cap, and let me bring this to the top. And we'll continue. Bring to front. Okay. And this P wave going through the layers inclined at 45 degrees, then it's going to give me an average property of the linear stiffness in a direction other than the vertical or the horizontal. And by working through the necessary equations, you can show that this P wave velocity, in addition combined with the other parameters that we measured, so for example, you see this is over here, BP45, BP45, and this is BP45, is going to allow me to calculate one of the missing stiffness parameters, which is C13. And now I do have the four coefficients, the five coefficients needed to fully identify and characterize a vertical transverse isotropic rock. You could also use some other more complex methods in order to obtain these parameters, all the Cij for the dynamic testing. And I have one example over here of a work of my own where, let me find it first. And right here, this is a work of mine with Gabriel, and this is, let me, again, I'm going to provide a reference later in the link, but this is SPWLA paper, and I don't remember the number, but this is the title, in which we use a combination of transducers that do not go from end cap to end cap, but also go transversally around the sample. And by doing that, we can also measure some of the other missing stiffness coefficients by measuring wave propagation velocities in different angles with respect to bedding. So by doing some of these more complex methods, you can also get by and characterize the stiffness matrix in order to fully characterize your VTI rock. All right, so at the end of the day, what we would like to do is to do something similar to what we did for our isotropic medium, and that is to establish relationships that, let me move this to later discussion. What we would like to do is to obtain functions that will allow us to calculate the static properties from the dynamic measure properties, usually also combining well logging measurements. And what we're going to have to do is, in general, something like this. We're going to have to relate a parameter Cij, which is static, to a parameter Cij, which is dynamic. And similar to what we saw before, we're going to see that these parameters are usually, if this is a one-to-one line, this data usually falls a little bit lower, and you can, for a given formation and a given site, you can obtain a correlation that allows you to calculate this parameter to go from dynamic to static for each stiffness parameter. So now there is not just one of these coefficients, FDS, but now you will have 5. And at the end of the day, what we would like to do is to obtain all of these static coefficients to populate a model at the highest resolution possible around the wellbore or in a given formation. Okay. One more thing to discuss over here, it's also how we relate these Cij coefficients to the Young modulus and Poisson ratio coefficients. Notice that for the static part, we have worked with measuring Young modula and Poisson ratio, but for the dynamic part, we have worked with measuring directly stiffnesses of the stiffness matrix. So these two are not exactly the same, and in order to mix those two or to obtain the Cij from the static part, you will have to use some relationships, which some of those equations are a little bit long to write, but I will share those with you, and these are available in, if I remember correctly, in this paper over here, where these are just equations, and they come from inverting the matrix. And as soon as you invert the matrix, let me find the equations, you can obtain, like you see over here, the dynamic Young modulus as a function of the stiffness coefficients, or you can do also the opposite, calculate the stiffness coefficients out of the dynamic modulus. Again, this is just math, and it's not difficult to do, and I'll provide the references so you can find these equations. All right. So with this, we're going to end this video, and in the next video, we're going to talk about how to quantify this anisotropy when a rock is strongly anisotropic or not. And also, we're going to see parameters that characterize that anisotropy, like, for example, the Thomson parameters, and also some models that allow us to predict such anisotropy.